My dear students, today we are going to discuss on the topic applications of MÖSSBAUER spectroscopy. So far, we have discussed about the basic principles, the three main basic principles, instrumentation part, the three main hyperfine splitting phenomena. Using this, the MÖSSBAUER spectroscopy find enormous applications in various fields. Before going to understand the applications, we have to learn why this MÖSSBAUER spectroscopy is not that much familiar like other conventional methods. See this periodic table, which is very elucidative. Using this periodic table, which is clear that not all the elements in the periodic table are MÖSSBAUER active. See the blue background elements. There are a very few elements which are MÖSSBAUER active, and other elements, those are red background. Those elements are producing gamma radiations necessary for this affecting this MÖSSBAUER spectroscopy, but they are not MÖSSBAUER active, just like cobalt 57. In Fe57, iron 57 MÖSSBAUER spectroscopy, we are using cobalt 57 as a source in order to generate iron 57 MÖSSBAUER active nuclide, but cobalt 57 is not a MÖSSBAUER active. And other elements, the other elements in the periodic table which are unsuitable for MÖSSBAUER spectroscopy. This is the major reason why MÖSSBAUER spectroscopy is not that much familiar, though it finds a lot of applications in chemistry, medicinal chemistry and biological field, geology, mineralogy and archaeology, semiconductor field, etc. Let's discuss on it. In chemistry, we are going to discuss 10 applications. In order to use the spectra for application side, applicable methods, we have to understand the hyperfine splitting phenomena like isomer shift or resonance line shift, quadrupole splitting and the Zeeman splitting or magnetic inversion. Using the result which we infer from the spectra, we can apply it for application part. Okay, the first application is isomer shift and electronegativity. In the case of antimony trivalent compounds, there is a linear relationship with the value of isomer shift with the electronegativity. See the table itself, which is evident that the electronegativity of antimony trifluoride, you all know that fluorine possesses the very high electronegativity, the tendency to accept electron more towards itself. The electronegativity value is 2.1. In that case, the isomer shift value, the native isomer shift value is very low there. That means the isomer shift value is high in the case of antimony trifluoride. Whereas in the case of antimony triiodide, the electronegativity is very less. In that case, the negative shift, isomer shift is very high. Right? So, using the isomer shift value, we can predict the electronegativity of antimony compounds. The second application is isomer shift and Curie point in order to study magnetic behavior. Curie point, Curie's temperature, which is an important factor in understanding the magnetic properties of elements. What is Curie point? We will discuss about magnetic properties of chemical elements in a separate class. Okay, Curie point is nothing but it's a temperature below which a paramagnetic substance converted into ferromagnetic, or a paramagnetic behavior changes to ferromagnetic. So this isomer shift value can be used to study the Curie point, and you should remember the point. Note that below Curie point, the singlet of an ion complex or an ion compound which MÖSSBAUER spectra we have collected, if it is a singlet, below Curie point, the singlet will split into sextet. Okay, that you should remember. Below Curie point, let me repeat again, below Curie point, the singlet of a spectra split into sextet. Okay, so the third application is ion complexes bonding. You all know that iron possesses various oxidation states, so it forms an enormous number of complexes and organometallic compounds and biological compounds also, right? So in order to understand the bonding of ligands with this central metal ion, or central ion or other elements, how these bonds are formed, all these data can be inferred from the spectra that we obtain. I have given two examples. The iron dodecacarbonyl compound, which is one of the important organometallic compound, and the structure elucidation is very difficult using conventional X-ray. But using MÖSSBAUER spectroscopy, it's an octahedral structure which is clearly identifiable. And sodium nitroprusside, which is a compound of which the structure of sodium nitroprusside is very difficult to predict using other conventional method, but the bonding of iron with nitrous oxide, NO, can be identified. There is a d pi p pi back bonding is there, which we can identify using MÖSSBAUER spectroscopy. That's the third application, bonding in iron complexes. Okay, moving to the fourth application, to study tin compounds on the basis of isomer shift. In this case, we are using tin 119. This is the isotope that we are used to study the MÖSSBAUER spectroscopy of tin compounds. On the basis of isomer shift, what is the speciality in the case of tin compounds? Tin 2 plus have a positive isomer shift usually, whereas tin 4 plus valency or oxidation state exhibit negative isomer shift. So if we obtain a spectra, we can infer if the result observed in the positive direction of isomer shift, we can infer that the tin present in that particular compound or the complex is having +2 oxidation state. If it is in the negative isomer shift value, we can infer that tin in +4 oxidation state. So this is a speciality in the case of tin compounds. Okay, and the fifth application is that to study the inductive resonance mesomeric effect in organometallic compounds with the support of hyperfine splitting. So let's consider the example of tin itself. Tin forms tin tetraalkyl compounds. So we can use the isomer shift and the separate electronic environment. In the case of inductive effect, we already have a class on this. This inductive effect, the tendency to withdraw electron towards itself, is an electron withdrawing group, and the tendency to release electron also. So in the case of alkyl group, it will have a tendency to release electron. As a result of that, what will going to happen? The electronic environment with changes, there occur certain splitting and isomer shift value also. So using this isomer shift value, we can predict whether the compound showing inductive effect, mesomeric effect or resonance effect, and we can use that value to quantify, to find the magnitude of that particular effect also. This is one of the important application of MÖSSBAUER spectroscopy. Okay, and the sixth one is checking the purity of gold. Very important. You all know that in the periodic table, not all the elements exhibit MÖSSBAUER active, right? So this gold 157 is a MÖSSBAUER active element. So this is one of the commercial application of MÖSSBAUER spectroscopy. In many of the jewelers, they are using MÖSSBAUER spectroscopy. A portable MÖSSBAUER spectroscopy is available now onwards, which is useful to find the purity check of gold element. So very minute, very trace amount of sample can be checked using MÖSSBAUER spectroscopy, that is, and the result will be very accurate and reliable. That's the important, that's the major cons of this MÖSSBAUER spectroscopy. The seventh application is structure determination of certain complex compound in organometallic chemistry and transition metallics. The example is, we have already discussed that iron dodecacarbonyl compound, which gives a 3 lines forming near octahedral arrangement, and the xenon oxide. Xenon oxide, the structure, the hybridization of xenon oxides are very difficult in theoretical manner, difficult to predict, right? So using MÖSSBAUER spectroscopy, because xenon 129. That's a MÖSSBAUER active element. The xenon 129 spectra can be used to identify the exact geometry of xenon tetroxide xenon O4, which is having a tetrahedral geometry, and the trigonal bipyramidal structure of xenon trioxide is XeO3. So these we cannot use conventional methods or conventional instrumentation methods to find out. So using MÖSSBAUER spectroscopy only, we can find these kind of complex structures of certain inorganic compound. The eighth application is to study the nature of chemical bond in sodium nitroprusside. See the sodium nitroprusside, the chemical formula, where one of the cyano group, cyano ligand, is replaced by nitro, NO group, right? So to study the chemical bond, we have already learned that MÖSSBAUER spectroscopy can be used to study ion complexes, right? The bonding in ion complexes. And this MÖSSBAUER spectroscopy can be used to predict what kind of bonding that between that particular ligand and the central metal ion, here in the case of iron. Here, iron is having a d pi p pi back bonding with the NO ligand, nitro ligand. So, nitroso ligand. So, as a result of that, this back bonding can be predicted, and the presence of this back bonding can be studied using MÖSSBAUER spectroscopy, whereas other conventional methods are very difficult to find out. So this is one of the important application. The ninth application is to elucidate the structure of chemical bond in crystalline and amorphous solid state chemistry. Yeah, there are single crystal XRD is there, and powder XRD is there. There are certain limitations for those instruments. Those limitations can be cleared by using MÖSSBAUER spectroscopy, which will provide a proper structure and chemical bonds in the crystalline and poorly crystalline or amorphous solids elements. The 10th application is measure the changes in chemical environment of nuclear, phase change reaction, etc. So you all know that it's all around. This MÖSSBAUER spectroscopy is all around that central nuclear, right? We can get the result as one, that nuclear, there is a disturbance happen to that particular nuclear, right? The absorber nuclear or the sample nuclear. So using this disturbance, we can infer those disturbance from the spectra obtained. Using that, we can find the chemical environment around that particular nuclear, the phase changes, etc., etc. Okay, so these are the 10 applications of MÖSSBAUER spectroscopy in chemistry field. Now we move on to the second part, the biological or medicinal application. We all know that Fe57 MÖSSBAUER spectroscopy is widely used. Do you know the reason? This is because there are a lot of elements, there are lot of biological systems which contain iron, and many of the complexes involve the central metal ion. So due to the presence of iron 57, sorry, there is I missed the E there, Fe57 in biological systems such as hemoglobin, myoglobin, cytochromes, ferritin, xanthine, Fe57 MÖSSBAUER spectroscopy find applications in studying the complexities in bonding in oxyhemoglobin and carboxyhemoglobin, CO2. If hemoglobin is bonded to a carbon monoxide or carbon dioxide, what kind of bonding exactly happened, which we can study using MÖSSBAUER spectroscopy, and sickle cell anemia, blood disorders, etc. The second application is analyzing iron containing proteins, can be used to compare the iron content in tissues from healthy people and patients with hematological malignancies. So due to the presence of iron in various biological systems, we can rely on this MÖSSBAUER spectroscopy, especially Fe57, iron 57 spectroscopy, MÖSSBAUER spectroscopy for medicinal usages. Okay, so the major isotopes, MÖSSBAUER active elements used in medicinal field are iron 57, Fe57, gold 197, cobalt 57, tin 119, samarium 153 MÖSSBAUER spectroscopies. So here the cobalt 57 used as a reliable MÖSSBAUER gamma radiation source. Okay, and moving to the third part, mineralogy, geology, and archaeology. So this MÖSSBAUER spectroscopy find major applications in these three fields. The first application is grain size determination of ferro and antiferromagnetic ion elements. What is a grain size? Grain size is nothing but every metal. A metal is consisting of a minute crystalline particles oriented in different direction, and these minute particles are called grains. Using this grain whose direction, size, and orientation can be used to predict the magnetic property, the minute magnetic properties, micro properties of a metal or a crystalline element. So the grains size determination of ferro and antiferromagnetic ion materials and minerals and iron oxides, etc. can be find out, which find application in mineralogy and geology also. Excellent tool in geology for identifying the composition of iron containing specimens including meteorites, moon rocks, and iron rocks in Mars. So if in astrophysics and astronomy also, astrochemistry also, once we get samples collected from the moon rocks or Mars, etc., we can rely on this MÖSSBAUER spectroscopy to find the exact composition of iron in these rocks. So in mineralogy, to determine the redox ratios, the spin valence state, site occupancy of atoms in crystal structure and minerals, etc. Fourth application, important information on the short range order of chemical bonding present in amorphous solids can be determined. This is very important application. The fifth, both qualitative and quantitative analysis of elements bearing mineral phases, both crystalline, poorly crystalline, and amorphous, where conventional methods such as X-ray fail to interpret. This is one of the important point to note down. MÖSSBAUER spectroscopy is not that much familiar, but it is used as a reliable source, a reliable technique. If the conventional methods such as X-ray, single crystal X-ray, which fails to interpret certain compounds, just like amorphous, poorly crystalline phases, etc. And the fourth application part is semiconductor field. The semiconductor field, when we consider the physics application in commercial manner, we all know that in the case of in the periodic table itself, let's see again, in the periodic table, we can see that the germanium in the boron family, carbon family, and nitrogen family, where germanium and antimony Sb both are both are used widely. Those are semi-metals widely used in semiconducting field. So in MÖSSBAUER spectroscopy is used for the characterization of magnetism in iron-bearing minerals. Excellent tool in studying microenvironment like magnetic interaction, magnetic ordering, types, etc. by determining the oxidation state, spin state, symmetry, etc. in for surface related matters. In the case of alloy formation, in all these cases, microenvironment like magnetic property, understanding of magnetic property is very important. To quantify super paramagnetism in magnetic materials. The third is to monitor the changes in the chemical environment surrounding the antimony nuclei during oxidation state changes, manufacture of diodes and infrared detectors, etc. These are the three main applications used in semiconductor fields. So, MÖSSBAUER spectroscopy find many applications in not only in chemistry but in medicinal field, biological field, and mineralogy, geology, archaeology, and semiconductor field, and commercially in checking the gold purity also. So if other conventional methods fails, MOSBAUER spectroscopy find its way to interpret many of the results that give a useful information. Okay, thank you very much.